We are now going to be looking at electrochemistry. Electrochemistry, the study of the interchange of chemical and electrical energy. We will be examining the chemical solutions and seeing how we can transform that into a flow of electrical current. And as you can see here on the nice slide, one of the main applications of electrochemistry is being able to use the battery, using a battery which will, inside are a bunch of chambers with the chemicals in here that will create electrical current to power devices. Now the way that we set these up in order to create the electrical energy from the chemical energy is by having the redox reaction. We're going to split them up into two half reactions. So the overall reaction is being split into two half reactions. You have, of course, your oxidation and your reduction reaction. So we're going to recall a little bit of redox here. Looking here at our overall reaction, and you can see the permanganate going to the manganese 2, because remember this is a +7 here for our permanganate for counting the oxidation states. So this one is obviously being reduced here in that process, and then of course the iron's going from +2 to +3. So this is going to be the oxidation half reaction. And noticing too, in this particular one, we have, it's an acidic solution because we have our hydrogens, of course, with the waters participating as well. But by splitting it up here, as you can see, we have the two different reactions, your reduction and your oxidation. And we're going to be able to isolate them and make it so that we can have a controlled flow of electrons that are going to create the electrical energy. This is what we want to see here, is being able to manipulate it so that we are going to be able to have a flow of electrons, and that's going to create our electrical energy. Now, splitting the half reactions into separate chambers, as shown here, this is what we would call a galvanic cell, but basically we're splitting our oxidation and our reduction reactions into two separate chambers, and by doing so, what we are able to do is, facilitate the change of the chemical energy into electrical energy by having the electrons, the moving electrons, flow in one direction. That's what's going to produce the electric current. And the way it runs is from the oxidation side over to the reduction. So the electrons always go from the oxidation chamber and flow over here to the reduction side. But being able to have those electrons move in one direction is going to be what produces the electrical energy, or what we would consider to be electrical current. And that's very, very important here in order to make sure that we are creating the functional battery that we are able to use the power for. Now, this setup I said was a galvanic cell. It also could be called a voltaic cell or an electrochemical cell. Sometimes they call it that. But it's a device in which the transfer of electron takes place through an external pathway rather than directly between the reactants. So that's the idea of this external pathway, is the wire that connects the two chambers together of the galvanic cell. This part right here said, this is the wire attached to these things right here, which are called electrodes, that are dipped into the solution. This is the oxidation side, this is the reduction side, and this is also an electrode over here. So the electrons are going to flow. And this is the external pathway that we're talking about. That external pathway is hooked from the different pieces that are taking place here in our galvanic cell. So now we're going to go ahead and outline and label the galvanic cell, the important pieces. So here showing, once again, the oxidation and reduction, and this is just a different type where they have this thing in between. It's usually called a porous disc. We'll explain the function of that later, but you can have them completely separated, into two separate beakers as shown in the previous picture, or separated chambers by a device in the center like this. And this is kind of how the batteries work. They have the separated chambers through this type of fashion. But you have the oxidation, the flow of electrons going from oxidation to reduction. But the important things to label here is the anode and the cathode. The oxidation side of the reaction is called the anode, important piece of information here, and the cathode is the reduction side. Now there's an easy way to remember this. We say anox and we say red cat. So reduction takes place in the cathode, oxidation takes place in the anode. So those animal references here. Now we used to say Leo the lion says grr, to remember the losing of electrons is oxidation, the gaining of electrons is reduction. Anox, the anode, is where oxidation takes place. Red cat is cathode, is where the reduction takes place. So answering our questions as we're looking here, what occurs at the anode of the galvanic cell? Well, that's going to be the oxidation reaction. What occurs at the cathode? That's going to be the reduction. Electrons will spontaneously flow from the anode to the cathode. As electron flows, what will happen to the overall charge of the anode? So if you're thinking about what's going on here is the electrons are leaving the anode and going over here to the cathode sides. So what you should see that's going to happen over in this side of the chamber is a bunch of positives are going to start building up. It's going to become more positive on this side. And what's going to happen then over here on this side? Well, because electrons are flowing to this side, which are negatively charged particles, that means that our lovely reduction side is going to become more negative, and negative charge will build up over here on this side of the cell. So we're going to get a bunch of negatives start to build up over here on this side. So in order to take a look here, those are the basic setup. Don't forget too that these are electrodes. They are solid, made of solid material that is dipped into the solution. And we'll talk about what the electrodes consist of in just a minute, depending upon which type of E-cell or what type of voltaic cell, galvanic cell you're creating. Now, with this setup, the system will start but then stop immediately. We need to think about why that is. The electrons here, remember this is the oxidation side, this is the reduction side for our example, and they are going to start flowing from anode to cathode. Anode over here, cathode over here. But it will only run for a few seconds if we, if we don't have another piece in our deal over here. Oh, that doesn't look very good. Let me restart. All right. So electrons start to go. We said this side's becoming more positive. This side is becoming more negative. And as it flows for just a few seconds, because this positive charge builds up over here and this negative charge builds up over here, what's going to happen is the electrons, of course, being negatively charged particles as they are going to start attracting back to the positive side. And it's going to cause a backflow, and the electrons aren't going to go in one direction anymore. We need them to flow in one direction to produce the electrical current, but if this side becomes more positive and starts building up, the electrons are going to start attracting back to that side. And then we no longer have our directional flow of electrons. So the system will stop working, and we will not have our battery working, and it'll seem like it's a dead battery. So as the positive charge builds up, electrons will will be attracted backwards and flow backwards. So we won't have our directional flow anymore. So what we do to counteract this and keep it flowing for more than a couple of seconds is we add in something called a salt bridge. Now the salt bridge can look like this. This is sometimes it's a glass tubing, and they put this paste inside there, so it's not a solution, it's a paste, so that it doesn't just immediately fall into the chambers. And as you saw on the other model, it could be that porous disc. So the salt bridge could also be a porous disc, as shown in the previous one, and they put the paste inside between the chambers and the porous disc. What is it for? Well, it's for maintaining the electrical neutrality of the solutions. And I'll show you how that works in just a minute, but usually made from soluble ionic compound. Now, I also want to stipulate here that it has to be something that will not react in the redox, that will not react in the redox reaction setup. So you don't want, if it's going to affect like the iron or the permanganate and it's going to react with one of those reactants, you don't want to use that type of salt. You want to pick one that isn't going to react with either components, cause any change in the flow of the electrons. These ions are inserted into a paste or gel that make up the salt bridge. Now, if we're looking here at our salt bridge, what could go in there? So for instance, we have, like we could put in like potassium solutions seem to be pretty inert, and they are not going to react with what's going on over here. So potassium nitrate's a good one, or potassium sulfate, okay? What you're going to see here that's going to happen is, inside the paste, they will be dissolved in the paste, so they will be broken up into their ions. You'll have your K pluses and your NO3 minuses. And because we remember this side's going to become more positive and build up since it's the anode, the nitrates, okay, because they have the negative charge, they're going to attract and go this way towards the anode and fall in. And it's going to balance out the charge in the anode, so keeping it pretty neutral, the neutrality that we're talking about. We want to keep it neutral. The K pluses, the cations, are going to go over here to the cathode, because this one's going to start building up and being more negative in its charge. So that cathode side's going to need some positives attracted. Okay, so those K pluses will come over here to help balance out the negative charge and maintain, once again, the neutrality. Because we need both chambers to stay pretty neutral in their charge, so that way the electrons will keep flowing in the direction that we want it to, so that we have an electrical current, and that electrical current will power whatever device we want to power. Now there's an easy way to remember this as which way they're going to flow. The components of the salt bridge, they will migrate, we say the anions are going to migrate towards the anode. Anions match with anode, so that's kind of a nice little trick. Anions of the salt bridge go towards the anode. The cations of the salt bridge go towards the cathode. So that's a nice, easy way to remember which way they're going to migrate. Cations go toward the cathode, anions go towards the anode of the salt bridge components. And of course, if there's no salt bridge, what you should know and realize is it's only going to last for a few seconds, and then the flow of electrons will stop and you won't have an electrical charge anymore. No voltage will be, no measurable voltage will be going through. So it's be sort of like a dead battery. So this is the main deal for the construction of the salt bridge, and remember, it can also be a porous disc between the two chambers, like so, like before on the other diagram, it was a porous disc between the two chambers, and that's where this is where the gel or the paste would be in there that holds the neutral ionic compound that can maintain the neutrality of the solution, where it's something that's not reacting with either of components of the oxidation or reduction reaction. So now what we're going to do here is practice. So you can take a moment, pause the video, label the galvanic cells that uses the following reaction. You'll want to figure out what's being oxidized and what's being reduced, so then you can label correctly. They drew in the arrows for you too, so you know which side should be which side, which way the electrons are flowing, and so forth. Okay, let's start looking at the oxidation reaction first. So we have our zinc, starts at 0, and it's going to go over here to +2, so this is definitely going to be the oxidation reaction. So zinc going to Zn2+. Now what you'll notice too is that the solid is part of the reaction here. So that's actually, this side is, because remember the electrons, they flow from the anode to the cathode. This side will be the anode. Now this electrode here, is a solid that's part of the reaction here. So this is going to be zinc solid. This electrode actually is part of the reaction, and you're going to have a solid zinc metal being the electrode here. And then you'll have the Zn2+ will start floating around in the solution as the electrons break free, because that's what's happening over here, is the electrons are breaking free. So we have the zinc solid atoms turning into the Zn2+, and you have 2 electrons going up here, up the wire over here to the cathode. Okay, now let's look at the reduction reaction over here. As you can see, this is going from the Cu2+ over here to the copper solid, which we know is going to be 0. That means you're going to be adding in the 2 electrons, and they are going to flow over here. And this is definitely, remember the direction of the electrons. Sorry. Go away. Stop. The flow of the electrons going in that direction over here. So this is going to be our cathode side. Now also the copper solid is a part, so we're going to identify the electrode, and this is going to be a copper electrode in here. The metal can represent that, and then the copper +2 is going to be in the solution. This will already be in the solution, ready to go. You have your copper solid here, so when the electrons come in, they'll combine with the copper 2+, and it'll attach. It's actually going to attach atoms, attach the solid atoms to the electrode here. So that also means that over here on the zinc side, the zinc solid atoms are actually breaking down. So this side is going to be getting smaller. It's going to, some of that zinc solid is going to turn into Zn2+ solution. So this electrode will start to get smaller, and some of the mass will degrade because it's turning into Zn2+ in solution. And that means over here, since we have the ones attaching to the copper here, that this electrode is going to become more massive. So you're going to end up building up on this side because the electrons combine with our copper 2, and then it forms a copper solid atom that attaches to the electrode. Okay, one more thing to add in, of course, is our salt bridge here. This is where we would put our soluble ionic compound that's not going to react in this particular case. So you could use, the the potassium sulfate, remembering, of course, that the potassium ions are going to flow towards the cathode. Cations go towards the cathode. The sulfate ions would travel towards the anode, and anions go towards the anode. So we would definitely want to make sure that we insert the salt bridge into our galvanic cell here, our electrochemical cell. Just to recall and go through the questions to make sure that we are looking here. How do you know which compartment is the anode? Well, here we're looking at the electron flow, or because we had to label this from scratch. We were looking at the electrons were going this direction. So we knew this side, it always flows from anode to cathode, like so. However, if it was already pre-labeled, where they already put the electrodes and the solution components in there for you, you would look for the side that has the oxidation reaction, and you would look for the side that has the reduction reaction. So that's two ways to tell. If it's not labeled, you would want to look at the electron flow. If it is labeled, look for the reaction. Oxidation is going to be in the anode, the reduction will be over here in the cathode. How do you decide on the electrodes? Another good point here. We look for the solids in the actual reaction. Now, sometimes the reactions aren't going to have a solid that's in them. Everything is going to be in ion or solution form. In those cases, if that were to be, you want to use an inert electrode. One that's not going to react, once again, with the overall reaction. So some good examples of inert electrodes are going to be carbon, which is really a graphite electrode, which is just carbon. And then the other one that's used quite frequently is platinum, because platinum's not a very reactive metal. Platinum, and that's going to be PT on the periodic table. So inert electrode, if you don't have a solid already up here in the reaction for you to use as your electrodes. What should you use as a salt bridge? You want a soluble ionic compound that's not going to react with either one. And for the most part, you're not going to have to choose this stuff. They're going to give you the diagram already filled out, and you just have to realize what's in the salt bridge, which way they're going to go. Cations go towards the cathode, anions go towards the anode. But this is what the choices that you would make. What electrode gets more massive as the reaction goes on? The one that gets more massive is the one in the cathode, because the electrons attach to the ions and form the solid. Over here, on the anode side, the one that becomes less massive, of course, is because the zinc is breaking apart into the ion and the two electrons over here. So it's going to start to break down over here. This one's going to become less massive as time goes on. Now, another thing to consider besides how massive the electrodes get, or less massive, I should say, for the other side, what happens to the concentrations in the components? So if you think about this, since this side is producing the zinc ion, the concentration over here should be increasing, getting higher, because you're making more of this zinc plus 2. And then the opposite is true over here on the reduction side. Since you're removing the copper 2, like it's part of the reactants over here to form the solid, the concentration of the copper 2 is actually going to decrease over on this side. It's going to go down. So the side that has the more massive electrode, the concentration starts to decrease. The side where the electrode becomes less massive is when the concentration is going to increase. So oxidation should get more of the concentration, less of the electrode. Reduction, you'll get more of the electrode and less concentration. So why might some batteries stop working? This is a really good question. Well, you could run out of any of these components. You could run out of the electrode, the zinc electrode, if that gets used up. You could run out of the copper solution. Over here on this side, if it decreases so much that you run out of it. Another thing to consider is the salt bridge components. If those get used up and there isn't anything left to maintain their neutrality of the solutions, of course, the electrons will start attracting back to the more positive side and stop flowing. So there are some things that can happen when why they might stop working. They eventually can't run forever because you are going to run out of reactants. And for the oxidation, the reactant happens to be the zinc solid. And for the reduction, it happens to be the copper 2 on this side. And of course, the salt bridge There's only so much you can put in there, and they eventually also will run out and won't be able to maintain the neutrality of the solution. Okay, so like this diagram, which is the same reaction that we were just looking at. Oops. Let's go back, apparently. The zinc solid plus the copper 2 giving you the zinc plus 2 giving you the copper solid. Same reaction we were just looking at. I like this particular diagram from the book because it also shows you the particulate model diagram. Down here, as you can see, the zinc atoms are becoming zinc ions and going into solution, and the copper 2 ions are being added to the electrons, and they are forming solid on this side. This is also showing like a porous disk in between. So you can see that that's where the salt bridge would be in this particular case. Another thing they put on here is the voltmeter. And the voltmeter measures volts or voltage. Voltage is measured in volts. So we use the big V for that. Another thing that you should notice while you're looking here is this is a cell, electrochemical or galvanic cell at standard conditions. They're going to have 1 molar solutions to be at standard conditions. So standard conditions, remember, talked about this in thermo part 2, but gases, are at 1 atmosphere, the temperature is at 25 degrees, and all solutions are at 1 molar. 1 molar solutions in order to be considered at standard conditions. So that's what you see here, and checking out this lovely particulate model diagram of how the reaction is taking place. So how do we know what is going to be spontaneously oxidized and what's going to be spontaneously reduced? Well, we look at something called the cell potential. The cell potential is important in and of the fact that it tells us or gives us the electromotive force. This is the driving force that moves the electrons in one direction. So that cell potential measurement is going to tell us what we can do to create our galvanic cell in order to make it positively flow in one direction and be thermodynamically favored. So the driving force on the electrons, substance being reduced, is going to pull the electrons over the wire to the other side. The substance being oxidized is going to be pushing the electrons across over to the other side. So it's a combination of the pulling of the reduction reaction and the pushing of the oxidation reaction that causes this electromotive force, or EMF. And that's how we can get the electrical current to go, the electrical energy to flow. Now, E cell is measured in volts, that voltage V, and we use the voltmeter to measure that. When you have a positive E cell, the positive E cell value tells you we have a thermodynamically favored reaction, and it will be spontaneous, and it will just start producing the flow of electrons on its own. It doesn't need any outside intervention. But you need to have a positive E cell for this to occur. We're going to talk about where that comes from in just a minute. So thermodynamically favored when the E cell is positive, and it would be spontaneous, and the electrons will just instantly flow from the anode over to the cathode, and you're going to have the anode pushing them because it's the oxidation side, and the cathode side pulling those electrons and getting them to come over. Before we get into the whole table of the standard reduction potentials, it's probably a good idea to know how they were calculated. Standard reduction potentials are measured value. They're in tables in the back of the textbook or online, but they come from these tables from the standard hydrogen electrode. So all of them, basically, every single one in the table were measured at standard conditions. So you see the 1 molar here, and this would be at 25 degrees Celsius. okay? And then the hydrogen here, of course, would be under the pressure would be 1 atmosphere. And this is how you would have to administer a gas, because obviously it'd be hard to put that into the solution. So they pump it in through this tube. And then they're also showing that the electrode, in this case, because the reaction for the hydrogen, where you're getting the H plus ions from the H2 here, doesn't have a solid component to it. So that's why the chosen electrode is going to be platinum here. So that's going to allow for the reaction to take place, because you have the hydrogen gas going in, you know, the H2, and it's going to produce 2 H pluses in the solution like so. But this is always going to be the cathode side in order to create these reduction potentials. So then over here, any other substance that was on the table was measured against the hydrogen, and then they measure it on the voltmeter and decide what the standard reduction potential voltage was in those cases. So this is how it was measured, was using the hydrogen electrode. And the standard reduction potentials look like this. You see them in a table format, and in the textbook, they are in, you know, the appendix part 2. You can find them there. And this should say reducing it cut off a little bit, but the weaker reducing agent to the stronger reducing agent, the stronger oxidizing agent to the weaker. Yes, it's in appendix 2, A13, A14 if you want to look at them. Now, for reference, these ones will be provided in the exam for you. They would not expect you to have anything memorized. Any reduction potentials that you would need for any of the problems will be given to you. Now, this table, they do it based off of the strongest oxidizer and the strongest reducer, okay, based on the reduction potentials. So if we're looking here at our reduction potentials, you have, say, for instance, the silver adding to the electron, giving you the silver solid. The reduction potential is 0.8. So by reducing our silver, okay, over here to our solid silver, it produced a voltage with the hydrogen of 0.8 voltages, or volts. I guess I should say volts. That's the correct word, volts. All right, now you could flip this and turn it into an oxidation reaction like so. We flip it, make it an oxidation reaction. However, then that means the sign flips. So it's going to be negative 0.8 volts. So as you can see, the two options here for the silver, it produces a positive E cell, or a positive E voltage here when it is being reduced. If you flip it and try to oxidize it, it does not. So this one definitely would be a better one at being reduced than it is at being oxidized. So if we want to talk about in terms of agents, since it's better at being reduced, it's a better oxidizer or oxidizing agent than being oxidized or a reducing agent. So that's one example here. When you flip it, okay, you just change the sign. Now, like delta H, if you reverse a reduction, you change the sign. We kind of talked about that. However, there is one other stipulation here. If you try to multiply through, okay, you double, triple, or cut in half the reduction reaction. So say we multiplied everything here by 2, like so. Multiplying through by a factor actually does nothing to the E cell or the E voltage. So you would not, this would still say 0.8. Even if we doubled it, if we tripled it, quadrupled it, cut it in half, it stays 0.8. There is only a maximum amount of electron flow that can go across the wire. And so cell potential happens to be an intensive property. So it doesn't matter the amount. It's going to be the same no matter what. Remember, extensive ones, it does matter the amount. But since cell potential is going to be the same regardless of whether you double, triple, or cut in half, it is considered an intensive property like so. So now let's go ahead and take a look at our reduction potentials here. We want to look at which substance is being the best at being reduced and which one is the best at being oxidized. Well, we look here at the top, since these are reduction potentials, the one at the top with the highest E voltage is going to be the best at being reduced. So our F2 going to, or excuse me, that would be plus the electrons because we're reducing it, plus the 2 electrons, giving you F minus and 2 of them. This is the reduction of the fluorine into fluoride. This one has the highest voltage on our table here, so this one's going to be the best at being reduced. It's a positive E. We call it E reduction, like so, E reduction. If you flip it, then you would just call it E ox, okay? So the reduction potential here, this one's going to be F2. Very good. Now at being oxidized. So as you can see on this table, since this is all these are all under reduction potentials, the one that's going to be the best at being oxidized is the one down here that has the highest negative E reduction, like so, because all we have to do for this lithium reaction is flip it. So if we do the lithium solid, is going to go to the lithium ion plus the electron. We're creating the E-ox, right? So then all we have to do is change the sign here. So this is going to be a positive 3.04 volts. So this one, the ones that are the most negative on the standard reduction potentials, when you flip them and they become oxidation reactions, they end up being the best at being oxidized. So it's going to be the, lithium is a great reducing agent, fluorine is a great oxidizing agent, but lithium is going to be the best at being oxidized here. Now I'm sure you know and have heard of lithium batteries, and lithium is a main component of lots of batteries because it is really good at being oxidized. Fluorine is a little bit harder to use in batteries because remember here the fluorine is going to be in the form of a gas, so it's probably why it's not easily harnessed into a chamber setup like that. So you don't hear about all these fluorine batteries, but you hear about the lithium batteries because a lithium solid is easily put inside a chamber and it goes into the ion when it's in the paste form or in the solution form. So much easier to harness and use lithium for batteries than it is for using fluorine. And look, we are correct. Very good. Now let's talk about being spontaneous or thermodynamically favored. This E cell must be positive in order to be thermodynamically favored. So that means if we have a positive E cell, we know our delta G is going to be negative because in order to be thermodynamically favored, delta G is negative. And we also know and compare that the KEQ is going to be greater than 1 because we're forming products, and then the KEQ is going to be larger than 1 for that particular comparison. So with that, we know a negative E cell, which is not thermodynamically favorable, or we would say thermodynamically unfavorable, is going to be a positive delta G because it's not going to be able to get started on its own. But that also means the KEQ is going to be less than 1 because it's going to be mainly reactants because it's not going to really get started. And last but not least, when the E cell is equal to 0, that also means delta G is equal to 0. You're at equilibrium, and that means that KEQ is equal to 1. So now we're merging the E cell and the electrochemistry with the thermodynamics as well, and equilibrium is all blending together. So you see many concepts now merging all together and can be utilized together. So there you have the lovely answers. Now for doing some practice. This is what we're going to do here. We have two reduction reactions written out for us. They gave us the E-reds here, like so, and give a complete description of the following galvanic cell, which reaction is in the cathode, which is in the anode. What is the overall balanced equation? That's a good thing to find, and we're going to label all the parts of the galvanic cell for this particular case. Now, a galvanic cell, once again, just to make sure we're all on the same page, is defined by being thermodynamically favored. If it says it's galvanic or voltaic or an electrochemical cell, you should be, thinking about, especially galvanic or voltaic. Electrochemical, I guess, is a more general term, but if it says galvanic cell or voltaic cell, it means it is thermodynamically favored and it will go on its own. It does not need outside intervention. An electrolytic cell, which we'll talk about in part 2, that's the one where you provide a power source and it doesn't go on its own. So galvanic or voltaic, those ones are always thermodynamically favored. So that means that their E cells, okay, the E cell is supposed to be positive. So you have to set it up to make sure and ensure that the E cell ends up being positive. So in order to make sure that we're getting a positive E cell, we have to look at our two reactions here. We have the copper 2 plus the electron giving us copper 1. We have the gold 3 plus 3 electrons. That's going to give us the gold. This is a solid, like so. I'm looking at my two E cells. I have to flip one of my reactions because one has to be an oxidation, the other one has to be a reduction. And this is the basic general equation here. So to get your E cell for the entire thing, it's going to be the E of the one being reduced plus the E of the oxidation. So you're going to flip one of them to overall get your E cell. This is what you would do. I'm looking at my numbers, and remember, I need to make sure that it's going to stay positive. So the one that I'm going to flip happens to be this top one, because when I add them together, that means the number should come out to being positive for the E cell. So we're going to go ahead and flip the top one. So we're going to get copper plus going to copper 2 plus the electron, like so. And that's going to make sure that this E red is now going to be negative 0.153 volts. So if we're going to do that, we'll scratch this one out. We won't be using that anymore for our example. So now we can calculate the E cell, right? That was one of the things we need to make sure in order to set this up right. So I'm going to go ahead and do that. Calculate our E cell. So we get the 1.500 plus the negative 0.153 volts here, and this is going to give me my overall E cell, which once again has to be a positive value in order to be a galvanic cell by definition. So our E cell is at 1.347 volts. This is the E cell. And do remember, this goes out 3 decimal places for both, so when you're adding and subtracting, that's what you would use for your significant figures. So now we have that, but it also wants a balanced overall reaction, and that's the key here too. So remember, for balancing, the important thing for redox is you have to make sure the electrons are balanced. That's the important part. The electrons are balanced. Looking here, this one only has 1 electron. This one has 3 electrons. That means I'm going to have to multiply this one through by 3. So this is going to be the 3 copper plus going to 3 copper 2 plus the 3 electrons, and then if I'm going to combine it with the other one, which I have gold 3 plus the 3 electrons, that's going to give me the gold solid here. As before, we will cancel out our electrons, but it's balanced based off of the electrons, so these cancel. So our overall balanced reaction is going to be these components. So we have 3 Cu plus, and they're AQ if they're in ion form, so don't forget that. I'll write it in just to make sure everybody's remembering that fact. And then we get 3 of our copper 2 plus, AQ, and the gold solid, like so. So this is the overall balanced reaction here for this particular one. Now it says label all of the parts of the galvanic cell. Well, we know this is our oxidation reaction. We know this is our reduction reaction. And we know, looking here, that the electrons are flowing in this direction. So over here, this is supposed to be my anode, like so, and this side will be the cathode. And I'm going to switch colors one more time so that we don't see any blending going on. So let's go ahead and go back to the bright red here. All right, so in this one, this electrode here, looking at our oxidation reaction, both of the components in this particular case happen to be ions in solution. So we're going to start off with our copper plus in solution over here, and this one needs to be an inert electrode, so this one might be, I'll make this one graphite this time. We'll make this carbon graphite for our electrode. And then over here on the cathode side, we do have a solid, so we would make this a gold solid electrode for that particular one, and you would have your gold 3 ions in the solution. So labeling those components here. The last component to label, of course, is the salt bridge. And like I said, you're not going to have to actually identify any particular component to put in here, but they might, they might have labeled for you. So, like I said, those potassium compounds usually do a good job here. So potassium nitrate, that means over here to the anode side, this is where the nitrate would migrate, because the anions migrate towards the anode to keep the neutrality, and then over here the cations would migrate towards the cathode to keep the neutrality of the overall balance, to keep the electrons flowing in that direction. And this is where you would attach a voltmeter if you were going to, in order to measure the flow of the electrons, which should be at 1.347 volts. So here is our E cell, here is our balanced overall reaction, and we have our nice labeled galvanic cell. Now for another practice, I'm going to go ahead and take a moment, you can pause the video, try to do it on your own. Figure out the balanced reaction, figure out what's going in the anode cathode, figure out the E cell, how to make this a spontaneous flowing E cell, and then you can label all the parts again, and we'll go ahead and go over it. Okay, so now I'm looking up here at my reaction. And I have my permanganate, the acidic solution, 5 electrons, the manganese 2, and the water. And I'm looking here, I have periodate, 2 hydrogens, 2 electrons. This is going to be iodate and water. But I'm noticing already that my electrons are not equal, so I'm definitely going to have to do some multiplying in order to balance this out. But let's figure out which one I need to flip first before I decide to multiply through. Remember, multiplying through doesn't change the E cell, but flipping does change the numbers. Now I'm looking here, both of my reduction potentials. In order to make this a positive E cell, Remember, it's consisted of the reduction plus the E of the oxidation. And I have 1.51 and 1.60 volts here. So I need to flip this one in order to make sure I get a positive number. So I'm going to go ahead and do that. I'm going to flip that one. The 4 water plus the manganese 2. That's going to give me permanganate plus the 8 hydrogens, this acidic solution, and the 5 electrons, and this is going to turn into EOX, which is going to be negative 1.51 volts. Now I'm going to also rewrite the other one below too, because eventually for balancing purposes, I'm going to have to multiply through to get my electrons to balance. So this is, I'll use I's. Iodate plus the 2 hydrogen plus the 2 electrons. That's going to give me that's the per iodate over there. Sorry, this is the iodate and the water. And then this is going to be E red, which is 1.60 volts. So we add those two together to get our E cell. And we're assuming this is at standard conditions. So this is going to be 0.09, I believe. Yes. So 0.09 volts. It's not, full-fledged, but it is above, is positive, so definitely will be spontaneous. Now let's look at balancing our overall reaction for redox. So I'm going to go ahead and multiply this one through by 2. This side is going to, or this particular one's going to be multiplied by 5 because I need a common multiplier for my electrons. So if I multiply the first one by 2, I get 10. If I multiply the second reaction by 5, I'm going to get 10. Remember, it's all about balancing those electrons for redox, not just balancing the coefficients of the elements. So this ends up being 8 water plus 2 manganese. And I'm just going to go ahead and do all of the reactants together. So this is going to be 5 per iodate plus 10 hydrogens. That's going to give me 10 electrons for the reactant side. So I took care of all of our reactants. Got them all multiplied. Now let's do the products here, which is going to be 2 times permanganate. So 2 permanganates plus 2 times the hydrogens, 16 H's and 10 electrons, plus down here we would get the 5 per iodates. No, these are iodates, sorry. IO3 is iodate. And then we're going to get 5 waters. So getting close over here to my cell. Now I set it up this way because now I'm going to have to cancel, right? Canceling both sides to get it down to my overall balanced reaction. So let's go ahead and do that. 10 electrons go. That's easy. But now we've got hydrogens on both sides, so I'm going to get rid of this and make this one 6 hydrogens. Oh, I also have waters on both sides. So this is going to go completely away, and this is going to turn into 3 waters over there. Now I'm ready to write my overall, so I get 3 water plus 2 manganese 2s plus 5 per iodates. That's going to give me 2 permanganates plus 6 hydrogens, 5 iodates. So here's our overall balanced reaction. Wow, that was quite a lot to get that. So we found our E cell and we balanced our reaction. Now we just have to label. It's very easy to do. We have our electrons going this direction. So this is obviously the anode for this diagram. This is going to be the cathode. We just kind of fill in what we need to fill in. What we should notice here too is that both of these reactions do not have solids involved, so we're going to have to use inert electrodes. because we have Mn here, the iodate, the periodate to iodate. So here we would say this one's going to be the graphite, and I'll make this slide over here platinum solid. Here's our salt bridge, which, you know, we've already talked about what goes in there, so I'm not going to relabel the salt bridge for this one. But the oxidation reaction, okay, so looking here, the oxidation is going to have the Mn2 plus in here, and the reduction reaction is going to have the periodate starting over here. Now, as the reaction runs, you're going to end up with product, of course, building up in here. As the reaction runs, the manganese 2 will decrease, and the permanganate will start to build up in here. And then on this side, the periodate is going to start to decrease in concentration, and then the iodate will start to build up in terms of concentration as the electrochemical cell, the galvanic cell, proceeds towards completion. And then you might run out of your solution components or the salt bridge components, which would cause it to have no more electron flow, and it will be at equilibrium. And when you have no electron flow in E cell is 0, delta G is equal to 0 because you're at equilibrium. Now you have a dead battery. So that is how you would work some of these problems. And setting up your galvanic voltaic cell. Remember, these ones are always spontaneous, thermodynamically favored. The next set, electro part 2, we will look at the ones that are not thermodynamically favored and go over a few other main components of electrochemistry.